So now I'll discuss about questions related to convolution integral, and what I could find on the web page will be discussed here. So this is the slide prepared by Professor Mark Fowler, and this can be easily found on the web page. So I'll be discussing his slides here because it was not good to copy paste because of the copyright issues. So it's better that we adhere to showing his slides what he has prepared. So here is a question that is required to be solved using convolution integral. So convolve these two signals given as xt and ht. So xt is the input to the system which has the impulse response given as ht shown here. The amplitude of xt is 2 and the duration for which it is having this amplitude 2 is from 0 to 2. And then ht has an amplitude of 3 varying for time 0 to 1. So we are required to convolve these two signals, and the result for the convolution will be the output yt. And as I discussed this before, that we'll be first obtaining or preparing the convolution. We'll be starting the convolution with the graphical approach by inverting ht and then bringing it from minus infinity to plus infinity. So first of all, we change the domain from t to tau. This is what we had been doing in convolution sum as well. Then we flipped ht, or we inverted this about the time domain, the vertical axis, and on flipping what we get is the signal h of minus tau as shown here. So it's written usually easier to flip the short signal. So this is again the same property that I probably discussed last time, and if I didn't, then we'll be discussing this in today's lecture, the property of the associativity. So what that talks about is that if x convolved with h, so this is going to give you the output y. So x convolution with h star h is equal to h star x. So this can go either wise. So you can in fact flip the signal input x and keep the impulse response h intact, and then perform the operation of convolution. So either ways you're going to get the same result, same answer. So after flipping the signal h, we, as I told you before, that we are going to slide the signal, and should be slid theoretically from minus infinity to plus infinity. And in the meanwhile, we'll try to figure out the overlaps that exist between these two signals, and the amount or the magnitude of that overlap would have to be drawn, and that amplitude will represent the output yt. So after flipping the signal h of tau, what we get is h of minus tau, and the duration for which it will be existing is now from minus 1 to 0. So if you so this is something that is some pertaining to the basics of the signals that we already know about. So we'll skip this part and we'll come to the solution where the exact solution starts. So one thing that I told you, that what are the limits from where we'll have to slide. In fact, we'll have to evaluate or calculate things. So I told you that the point where this calculation should be started is that this portion, the rightmost portion of h and the leftmost portion of x, when they start overlapping, while h moves from left to right, in that case we will start having the convolution output on y when these two edges start overlapping. So let us so we will be having three conditions, in fact four conditions. The first condition is that when h is on the left side in such a manner that no overlap exists between h and x, so in that case the convolution result is going to be 0. So that's understood. So this is the situation. Let's call it as situation 1. And then there is the other situation 2, when we'll be having the impulse response h that overlaps with x, but there is not sort of completely overlapping, or let's say that the overlap of the right edge of h started, and we talk about the duration of overlap when h was sliding towards right, and then the left edge of h uh, came just below the left edge of x. So this is the second case, and the time for which this is going to happen is, since the width of h is 1 second, which means that if you say that h was slid from 0, then to 1 second it should be slid in order for it to for its leftmost edge to come just below the leftmost edge of x. So we talk about the duration in this case as 0 to 1. The first case was the time when t was less than 0. Then we have the second case when the time is from 0 to 1. The third case is that we'll be having the h and x overlapped in a manner that there will be a maximum overlapped area, and this is possible when the leftmost edge and the leftmost edge of h and edge of x, so both their left edges, they are just below the edge is just below x, and then the signal for h slides toward right and reaches a point when the rightmost edge of h comes below the edge of x. So this is the duration when t lies between 1 and 2. Then the third case is when the pulse corresponding to h will come out, a portion of it will be now coming out of the pulse of x. So this the duration for this will be corresponding to time lying between 2 and 3. So you can think that when the right edge of h comes just below the right edge of x, so this is the time when we have t equal to 2, and when h slides toward right, then at t equal to 3 you will be having the left edge of h just coming below the right edge of x. So the time duration for which this partial overlap happens is t lying between 2 and 3. And the final case is when there will be no overlapping between these two signals, and this is going to happen when time is greater than 3. So these are in fact, 5 cases. So 5 situations, the situation 1, 2, 3, 4, and 5. So now we'll try to use these situations to evaluate the final output. So as I told you, that convolution integral computes the overlapping area between the two signals x and h. So that the magnitude of that overlapping area will be plotted and will be representing the final output y. So now let us begin with the first case when no overlap exists and the signal h is drawn before x. So in that case, if you use the convolution integral formula, which is written again here, so you will observe that we are talking about the time when t is less than 0. Since the convolution integral deals with yt minus infinity to plus infinity, in that case, since you are going to have the overlapping between these two signals as 0, and thus the output y will be 0. So we are going to also change the limit from minus infinity to 0. So for minus infinity to 0, the overlap will be 0, always 0, and that is why we are going to get yt as 0. The second case is when we are going to have partial overlap, not complete, the partial overlap situation. And here we will be talking about the limit on time from 0 to 1. So this limit minus infinity to infinity, in this case we are going to substitute limit 0 to 1. So here they have substituted from 0 to 2t and then evaluated the functions. So what they get is 6t, and if you substitute the values, the limits from 0 to 1, that in that case you're going to get this as 6. The maximum value will be 6. So what does this mean? So in fact, what yt is now obtained in terms of t. So 6 is the case you started from 0 when there was the partial overlapping between these two signals just a start. So that was the case when the area started rising from 0. and will reach a maximum of 6 at t equal to 1. Thus the function that it will be following is 6t. So if you're not going to substitute t equal to 1, then you are left with the function 6t, and this holds between the time 0 and 1. So this is for time lying between 0 and 1. And if you plot this signal, what you're going to get is a line, a straight line that will be having a slope of 6. And it will reach a maximum. It will start from 0. So if you substitute t equal to 0 here, you get this as 0, y is 0. And the maximum will be t equal to 1 substituted here, then yt is 6. So you'll be having a line starting from 0 to 6, between 0 and 1, time 0 and 1. Then the second case is when time, so we divided these case situations depending upon the time. So the third situation was when t was lying between 1 and 2. In that case, we had a sort of complete overlap, the maximum overlap, not complete overlap, rather a maximum overlap that could occur between these two signals. So if we now talk about the time from t minus 1 to t, which is what we get after for ht minus tau. So this is ht minus tau, and this is the time t, the point t, and this is t minus 1. So if you substitute t minus 1 to t, and what you have the value of x tau s2 and ht minus tau s3. So if you substitute 2 and 3, you get this as 6. So this is what something done in the previous case, and I forgot to mention this. So the 6 was obtained from the magnitude amplitude of x as 2 and the amplitude of h as 3. So now if you evaluate this function, what you get is 6, simply as 6. And this is because if you look into this particular situation, so you will observe that when h slides from a point where its left edge and the left edge of x are just lying on one line, then as h slides and reaches a time 2, then the overlap between these two signals will be always constant. So this is the region between t equal to 1 and 2, where the overlapping area between these two signals will always be same, constant, and that is 6. So yt will always be 6 between t lying between 1 and 2. Then the fourth situation is when there will again be a partial overlap between these two signals corresponding to the time t lying between 2 and 3. Then we'll be again evaluating this, assuming that t is this signal is t, this point is t, and this is t minus 1. So but this overlap has to be done for the duration from t2 to 3. So if you are going to substitute the values from 2 to 3, then in fact you will be getting two situations. One is that you will be having a situation t minus 1 to 2, and the other will be 2 to 3. The case where you're talking about the limit 2 to 3 is the place where you are not going to have a sort of overlap between x and h, and that part will be will get 0. So it's not shown here, but the second limit is not written, but you will have to know this, that the value corresponding to the limit 2 to 3 is 0, and what we are left with is t minus 1 to 2. So now what we are going to get the function yt as minus 6t plus 18, and this will hold for the time duration 2 to 3. Now if you if you try to plot this for the duration 2 to 3, if you substitute this, the value of 2 in this expression, what you get is minus 12 plus 18, which is 6, and the upper limit 3 when substituted is 6. Minus 6 into 3 is minus 18 plus 18 is 0. What it means is that since you left yt at the amplitude 6, at the value 6 for t lying between 1 and 2, and for t lying between 2 and 3, you have the initial value of y as 6. So it will be starting at the same point where you left in the previous situation, the value of y, and will reach 0 at t equal to 3. So we'll draw the complete graph at the last slide. So they have drawn it. And the final step is when t is greater than 3. This is the situation when there will be no overlap between x and h. In that case, you are going to get the value of y as 0 always. So if we now bring all these situations all together, so the region 1 or the situation 1 when t was less than 0, so yt was obtained as 0. For situation 2 we had yt equal to 6, the minimum value was 0, the maximum value is 6. If you substitute 0 and 1 here, you get the minimum and maximum of y. And the situation 3 is 40 lying between 1 and 2. So if you substitute 1 and 2, so you would always get the value as 6. The fourth situation is t lying between 2 and 3. If you substitute this, as I discussed, it will start at the magnitude of 6 and will die to 0. Then the final situation is that you are going to get the output yt always at 0. So now we'll discuss about the properties which are associated with convolution integral as well as convolution sum. So the properties that will be discussed here holds for both the types of convolution sum and integral. And I use these slides of Professor Siripong Hortisu. So skipping all this and moving on towards the properties. So properties of convolution and integral. So one of which is commutative property, which says that h convolved with h is equal to h convolved with x. So they are always going to lead or result in the same answer. So it's immaterial if you're going to flip h or if you're going to flip x. So they will be resulting in the same y. The second property is distributive property, and it says that if x is convolved with the sum of h1 and h2, so this is equal to x convolved with h1 plus x convolved with h2. So this could be thought of through the given block diagram, where you have the system with impulse responses h1 and h2 added together and x given as input. So this represents the left hand side of this equation. So x is the input, h1 plus h2 is the total impulse response of the given system. Then the output y will be x convolved with the impulse response given here. So this is similar. This is equal to the two individual blocks h1 and h2 represented in parallel fashion and x given as input. So x will be convolved with h1 added to x convolved with h2, and this will be leading y output. Then the third property is associative property, where we have x convolved with h1 and then the convolution of these two terms will be convolved with h2. So this will result in x convolved with the convolution of h1 and h2. So in order to understand that how this is happening could be perceived through the block representation given below. And similarly, there is another term that if x is convolved with h2, so this has a similar understanding. So if you're going to convolve any signal with a second signal, and then this convolution result is convolved with the third signal. So it's like convolving the second and third signal together, then convolving the first signal with the result of these two, the convolution of these two signals. So graphically or using block diagram, this can be understood that if suppose xt is the input given to a system having impulse response as h1, and let's say h2 is the impulse response of another system which is fed with the output of the first system. So the output of the first system is what? Is the convolution of x with h1. So let's call this output as z. So if z is x convolved with h1, which is this part. So if this part is termed as z, then z convolved with h2 is output y. So in other terms, if we have h1 convolved with h2 first, then we convolve x with the resultant of these two. Then again we are going to get the output y. So this is shown in the figure below. So h1 is convolved with h2, and if x is fed to it, then you get this as y. And likewise, since associative property holds, so this can be written y in otherwise fashion. So h2 convolved with h1. so it's equal to this thing. And if you feed x, so what you get is again the same signal y, and this can be broken to be written as h2 on the left side and h1 on the right side, and this is what the second term is showing. So you have all these four terms equal. Then we have more properties like causality. So the term, this property says that the impulse response of a causal LTI system may be zero, must be zero before the impulse occurs. So if impulse is not present, or if before any occurrence of impulse, you will always have the impulse response of the causal LTI system to be zero. Then you have second point as causality of a linear system is equivalent to the condition of initial rest. Then the next property talks about the bounded input, bounded output, Vigo stability. So a necessary and sufficient condition for a continuous time, linear time invariant system to be Vigo stable is that the impulse response is absolutely integrated. So this is something that if I remember correctly, was discussed in Unit 1. So where we said that the impulse response is going to be, the system is going to be stable if you have the impulse response integrated and the result is finite, not infinite.